Hi guys, welcome back. We have just discussed the first few corollaries to the Hahn-Banach theorem, the first of which is still displayed here on the slide. This is a typical reformulation of the Hahn-Banach theorems in normed linear spaces, asserting that given linear functionals on subspaces, you can extend them to the full space in such a way that it's really an extension, so capital F of y is equal to the small f, and that the operator norms coincide. All right? That is a paraphrasing of Hahn-Banach. Now the first important corollary is this one about the existence of sufficiently large dual spaces. Namely, if you have a nonlinear space, then for any point in the space you can construct linear functional that is equal to the norm of that vector at the point and which has operator norm equal to 1, right? So in particular, this means for any non-zero point x naught, you can find functional that does not vanish at that point. So the dual space is really large. Now the next corollary that we will discuss here now is kind of curious if you think about it. So here we go. So now let x be a normed linear space and y a, now for the first time here some functional analytical things show up, so a closed subspace, and x not a point in the complement of y. So here we again implicitly assume that y is a proper subspace of x, so that such a point exists. And what it says is there exists a linear functional that vanishes completely on that subspace. So in other words, the kernel, so the kernel can be quite big. Y, I mean, okay, I shouldn't talk about dimensions, but y can be really large already. But at that point in the complement, the linear functional does not vanish. So some weird thing, you have here something closed inside. Okay, these pictures of course are deceiving. And maybe here's your big X, here's a point, and you can construct, well, not explicitly, but at least such things exist. You can construct linear functionals which are identically zero on the whole thing y, but outside not so much, because at least at one point they're different from zero. And these are linear functionals. Okay. All right, good. So this requires some longer proof. So we first show that there exists a constant C positive, so that y plus alpha x naught is at least C times complex modulus absolute value of alpha for all scalars alpha and the vectors y in the closed subspace. How to do this? Define G, sort of extending y by just this one vector. This is something that we saw in a proposition leading to the proof of the real Hahn-Banach theorem. So you look at this, so the sum of y plus alpha x naught. So you take a sum of a closed subspace with a one-dimensional subspace, and you define the linear functional by g of y alpha, g of y plus alpha x naught, just as the scalar alpha. Okay, then first note that G is well defined. We had to do a similar argument in the aforementioned proposition that leads to Hahn-Banach. Given that every z in y naught is of the form z is y plus alpha x naught for some unique y in y and alpha in f, right? Why this is so, this I explained in the proof of the proposition of Hahn-Banach theorem, because if you have two well, then you have this game again here, y1 plus alpha 1 x naught plus alpha 2 x naught. So you bring the y's to one side and the alpha x naughts to the other side. And then since y is a subspace, alpha 1 minus alpha 2 x naught has to be in y. If alpha 1 minus alpha 2 were not equal to 0, you would be able to divide out that scalar and you would conclude that x naught is in y, which it is not by assumption, it's in the complement. So what happens is that difference alpha 1 minus alpha 2 is equal to 0, so the alphas are the same, and then of course the y's are the same. So the representation is unique. It's the exact same argument that we used before. All right. Moreover, G is linear. Well, again, this is trivially true by construction because, okay, maybe this I write in color. So because if you have gy1 plus alpha 1 x naught plus y2 plus alpha 2 x naught, then by definition, this is, because you can, inside here you can add, you can bring these two together, so this would be alpha 1 plus alpha 2, but this is by definition, again, g of y1 plus alpha 1 x naught plus g y2 plus alpha 2 x naught. Right, so this works out, and you can decorate those two sums here with any scalars that you want. The argument still goes through. Okay, so it's clearly linear. Fine. What else? And well, g of y vanishes. G of y vanishes on all of y. Because why? Well, because each element here has this unique representation y plus alpha x naught, and when that element is already in the subspace, then the scalar alpha has to be equal to 0, right? Because this decomposition is unique. So, but then if alpha is equal to 0, then g of y plus alpha x naught, alpha being 0, is equal to 0. So that's true. Okay. Finally, G is a bounded linear function also. That's the one thing that still is outstanding. So how do I show that it's bounded linear? Well, that's where you now have to use that you're working with a closed subspace. So we will use that our very first theorem about equivalences between between linear transformations being bounded and continuous, right? That's equivalent when you work with linear objects. So that's what we will do here. We will show that that thing is continuous, actually. So we'll take sequence for if Zn, so that I can represent as Yn plus alpha n x naught in y naught is convergent, say Zn goes to a Z infinity, which I again can represent as y infinity plus alpha infinity x naught, then first off, okay, maybe allow me to restructure that argument. So this is convergence, so I have a limit as n tends to infinity. Then I claim that Z infinity is again in y naught. Why is this? Because you take a closed subspace here, y, and you add to that a finite dimensional subspace, right? And finite dimensional subspaces are in particular also closed. And that is a fact of life, that if you have a closed subspace and you take the vector sum with a finite dimensional subspace, then the resulting one, that y0, will be again closed. This is in general not true if you work with infinite dimensional spaces. So in other words, the sum of two closed subspaces is in general not closed. It works here because one is closed and the other one is finite dimensional. That will do the trick, okay? And that's what I'm using here. So then it's closed, and hence it has the following representation: Z infinity is equal to y infinity plus alpha infinity x naught. That's what I'm trying to say, okay? But this implies This implies, okay, so we have alpha n, of course, will then converge to alpha infinity as n tends to infinity. But what is alpha n? Well, by definition of G, this is G yn plus alpha n x naught. And what is alpha infinity? Well, by the definition of G, it is y infinity plus alpha infinity x naught. And there you have it. That is precisely the continuity of G, right? Sequence of elements converges to a target, and then the image sequence converges to the corresponding image of the target, right? That's precisely what's here. So continuity follows, all right? Let's write it down. And so G of Zn goes to G C infinity as n tends to infinity. It is G is continuous and hence bounded by our very first theorem, because we already established that G is linear. Okay, good. So this verifies our initial claim. Remember what the initial claim was? Verifies our initial claim, because what does boundedness of G mean? Well, and the boundedness of G is precisely that G of y plus alpha x naught. Is this a linear functional? Is this at well, less than or equal to, say, 1 over c y plus alpha x naught? Yeah, but if you remember what the definition of this guy was, this is equal to alpha, right? And then you only have to bring that c to the other side, okay? And then you have your initial claim. The initial claim was that the norm of y plus alpha x naught is at least c times alpha for some positive c. And that's precisely what we established there, right? Okay, good. Fine. Now having this, moving ahead. We introduce now the actual objects that we want to apply Hahn-Banach to via, so h will be y plus alpha x naught as c times alpha, okay? And note that h of y is identically 0 on y, again, because this decomposition into y plus alpha x naught is unique, so that only here works for c alpha equals to 0, and then h is equal to 0 by definition, as well as hy plus alpha x naught is less than or equal to, well, c times alpha, and that's why we needed that initial statement, right? This here, this green stuff here, because now I'm going to use it. So it will go enter in here, because now c alpha is at most y plus alpha x naught, right? Good. So this means in particular, so h is a linear functional on y star with operator norm at most equal to 1. And the well, first corollary to the Hahn-Banach theorem, that was what I called paraphrasing Hahn-Banach in terms of norms and normed linear spaces. So that first corollary yields existence of a linear f from x to f with operator norm equal to h, so the extension has operator norm equal to the operator norm of h, which is bounded by 1. They match on the subspace, so f of y is equal to 0, on y, and, well, f of x naught, well, f of x naught is precisely equal to c, which is different from 0, right? Because this corresponds to, remember, the value x naught, you can look up here in the definition, it corresponds to y equals to 0 and alpha is equal to 1, right? And then you plug it into the thing and you get precisely c, which is different from 0. All right, and this completes the proof. Okay, so this is, that corollary is that remarkable thing that you have, if you have a closed subspace and an element in the complement, then you can find a linear functional which vanishes identically on that closed subspace, but which is non-zero at the point which is in the complement. Okay. Now, if you drop the closedness, then in general, of course, this is no longer true. But the next best thing is what's stated now in the next corollary. So let X be a NLS and Y a non-empty subspace of X. Then, so in general not closed, then for every X in X with, well, positive distance to Y, so the distance is just, well, the infimum over those norm differences. If that distance is delta positive, there exists linear functional on X with norm at most 1. Okay, that's like in the last corollary. F of x is equal to delta at that point, and it vanishes again on all of y for all y and y, right? So as long as you stay away a positive distance from that subspace, things more or less work out like in the previous corollary, all right? But here this doesn't require that that subspace is closed, okay? So how to prove? Again, we start with the following trick. Proof. Again, we start with y0, which is y plus alpha x. That's a subspace. Now in general it's not closed because y is not assumed closed. But now define g, linear functional on it, by, well, g of y plus alpha x is equal to alpha delta. So again, you have to go through the same reasoning. This g is well defined because the decomposition of an element in y naught into y plus alpha x is unique, right? So here earlier that was x naught was in the complement. Now here you use that. That's why you need a positive distance between the element and the subspace, so that this decomposition in particular is unique. Okay. So this function, excuse me, is well defined. So let's write this down again. G is well defined. Okay, it is linear. That's the same computation I did earlier in yellow. It vanishes on all of y because the representation is unique. So an element in y would correspond to alpha equals to 0. And then you see by definition that 0 times delta is 0. So that is true. Maybe I should write this a little bit nicer here. G of y is equal to 0 on y. G of x when alpha is equal to, well, 1 is equal to delta. That's written here. These two follow from here. All right. And G is bounded. So how do we show this? Well, earlier there was this argument with the sequence and using the closedness. So now here it's actually easier. So gy alpha x is alpha, it's the scalar, delta is already positive, so I don't need the complex modulus or absolute value around it. But now what is delta? That's the distance between that point x and the subspace y. So it's this one. Yeah, but now if you remember how you compute an infimum, infimums are scaling invariant, because after all these are sort of optimized distances, so you can pull the alpha in there. Then you put it inside the norm, so you have alpha x, and then I would have to write here, well, strictly speaking, alpha y, right? Alpha y, yeah, but y is a subspace. So if I optimize over the whole subspace, I don't need to carry that alpha there out front, because I still got to run through all the vectors, right? So here that alpha actually you can drop. So you have this, y and y, okay? And well, sure enough, this distance, which is an infimum, so a lower bound, is, well, at least alpha x, say, plus y, okay? That's clear, because it's an infimum, it's a lower bound, right? Yeah, but then what you have here, I wrote now here in a different way. So gy plus alpha x in complex modulus is at most y plus alpha x. So this means that the operator norm of g cannot exceed 1, right? So g is at most 1, and that's why g is a bounded linear functional. Hence, this is again by the first corollary to the Hahn-Banach theorem, by the first corollary to the Hahn-Banach theorem, there is extension, bounded linear function on x, that f of y in such a way that f of y is equal to g of y, which is equal to 0 on y. We have f of x is equal to g of x, which is equal to delta, since, well, they align on the full subspace y circle. So in one case you take alpha equal to 0, in the other case you take alpha equal 1 and y equal to 0. So you have this for all c in y naught, and the operator norms are the same. Yeah, but the operator norm of g cannot exceed 1. So that's everything that was claimed. This completes the proof. Okay, so this works out as well. By the way, here, that last argument here that they match on that delta here, this, by the way, the same argument that you have to use, maybe this wasn't clear earlier now that I think about it, to get this equality here, right? Because that functional small f, it matches onto h on all of y0. So to get the element x0, you take y is equal to 0 and you take alpha equal to 1. Right. That's why f of x0 is equal to z, which is different from 0. Okay, good. That's the puts a lid on that. Now one more corollary, which is kind of famous actually, if you think about it. So this is the separation property. That's at least what is what it is known under. So for every two vectors x that are different from one another in a NLS, in a normed linear space, either real or complex, there exists in an NLS X, there exists, well, linear functional that separates them, right, such that f of x is different from f of y. Okay, that's why separation property. It's very much like in topology if you know something about Hausdorff spaces, that if you have 2 points, then you can separate them from one another. And here we achieve the separation through an element in the dual space. Okay. All right. That proof is super easy. Well, at least with what we have prepared already. If you don't have those preparation, that's quite hard. So set x naught as the difference, which is different from 0, then by that corollary about being able to construct linear functionals that don't vanish at those points. So this was the second corollary that we proved in this video. It was if you have a non-zero vector, then you can find bounded linear functional that is non-zero at this point. That's what we're going to use. And then we can find f bounded linear with well, f of x naught different from 0. Yeah, but f of x naught, because it's linear, this is f of x minus f of y being non-zero. Okay, and that's precisely what was stated there. All right, that you can separate. Okay, now the last consequence of Hahn-Banach that at least we will discuss here in the lecture. The exercises will have more corollaries. I will just state it and then we will prove it early on in the next video. So if you have a Banach space, now this surely now is very much functional analytic. Let X be a Banach space, either real or complex valued. If it's dual space, X star is separable, then X is separable. Okay, that will be a mighty useful thing to have. Not at the moment, but later on we will understand why this guy is so useful. Okay, good. So we discussed a bunch of consequences of the Hahn-Banach theorem. This one here, that theorem, will be the last of those. And very soon, right now you might not, understand why these consequences are of importance. I tried to illustrate them a little bit, but okay, so what? Nevertheless, we will see them in action when we prove, well, big theorems that are still to come. All right, I'll see you soon.